Hello, everyone. It's an absolute pleasure to welcome all of you on our webinar. I'm Vinay Singh, Loss Prevention Officer at West, and I'll be co-hosting the webinar today with Septon Carter-Hodemaker, Managing Director from Maritime Battery Forum. We are very delighted to host a three-part webinar series in collaboration with Maritime Battery Forum titled Debunking Myths About the Safety of Lithium-ion Batteries. Through the series, we aim to raise awareness within the industry about the risks associated with their carriage on board vessels, the safety measures which can be implemented on board to manage the risk, and also to discuss the advancement in battery technology, making it a reliable and sustainable option. Today's webinar is first part of the series and will focus on the safety implications of lithium-ion batteries carried on board the vessels, and will cover best practices for their handling and transportation, supported by case studies and recommendations from the EU LASHFIRE project. Before we dive in, here are a few housekeeping items. Please ensure your microphone is muted to minimize the background noise, and also feel free to use the chat function, which is at the bottom of the screen, to ask any questions. We will have a dedicated Q&A sessions at the end, so there will be plenty of opportunities to raise your questions at that point in time as well. Now, let's get started. For panelists, I'm very delighted to welcome our panel of speakers today, who are experts in their fields and are very ready to share their invaluable insights. On the panel, we have Septon Carter-Hodemaker, Managing Director, Maritime Battery Forum. In his current role, Seb focuses on the promotion of batteries in the maritime industry and supporting the sector with all battery-related challenges. Seb has worked in the research and development department of a prominent shipyard in Norway, where he performed research on aging of batteries in electric vessels, developed a battery sizing and selecting method, and worked on the design of many different types of battery-powered vessels. Seb is a qualified marine engineer. And we have Anna Karlsson, Project Manager, RISE Research Institute of Sweden. Anna specializes in ship fire protection and has worked extensively with fire safety related to ro-ro and container ships. She is currently leading a research project at RISE, investigating the safe transportation of EV on PCTC and ro-ro carriers. Anna has experience in conducting alternative design analysis in compliance with SOLAS and provides a valuable expertise to Swedish Flag Registry with fire safety-related issues at IMO. Anna holds a degree in fire protection engineering. And we have Mejdi Kumon. He's a principal engineer at American Bureau of Shipping. Mejdi is expert in battery-related technologies and is trained in both experimental and computational research. He's highly experienced in design reviews of life-critical systems, including manned underwater vehicles, launch and recovery systems, lifting appliances, pressure vessels, general cargo containers, MEGCs, and portable tanks. He is now part of the Machinery, Electrical, and Systems Engineering Group and Corporate Division of ABS. Mejdi holds a doctorate in mechanical engineering. So today's agenda, we will cover discussion on a fire safety perspective of lithium-ion batteries, which will be presented by Anna Karlsson, followed by safe transportation of EVs on board vessels, which will be presented by Mejdi Kumon. Thereafter, we will have a short panel discussion on the topic and followed by Q&A session with the audience. Without further ado, I'll pass on to Anna. Anna, it's all yours.
Thank you, Vinay. I will share my screen. Like this. Thank you for this introduction. I am, as you mentioned, working at the RISE Research Institutes of Sweden, and just to give you the idea of what this is, it's the state-owned institute in Sweden. It's a non-profit organization with more than 3,000 employees, and we do have a fire and safety department since the 70s. And we have large fire halls and battery safety lab where we do have tested lithium-ion batteries since the 2000. Me and my colleagues are working a lot with the electrification in the shipping sector. And during the years, we have carried out a number of projects related to carriage of batteries and alternative fuel vehicles. And with this, we have increased our knowledge, and I hope that I today can increase your knowledge by sharing our experience. And yeah, you might have heard of the LASHFIRE project. This had a specific focus on ro-ro ship fires, or fires in the ro-ro space on the different ro-ro ship types. And you can find the deliverables and the reports from there at the lashfire.eu. We have finalized some guidelines and the 2-pagers, but also heavy reports. Other research projects that we execute is published at DIVA portal. So everyone has seen it on the news. Fires in lithium-ion batteries, electrical vehicles, they are reported frequently in media. However, we know that a number of vehicles started in the traction battery of an electric vehicle are actually rare. In the background of this slide, you see a burning vehicle, and this has no traction battery included. So there are still some misconceptions out in the public, and I will share you why do we actually have vehicle fires, and now I'm talking about the vehicle in general. So looking at land-based fires, we can see that arson actually has a high proportion of fire starting the fires in the vehicles. But looking at the ship fires and investigations that also RISE has carried out on vehicles and passenger cars, and specifically, we see that electrical faults are a common cause. And more than 60% of the fires in a ro-ro cargo space actually has electrical cause. And this includes, for example, short circuits, the 12-volt battery, and the reefer units. It's mainly the cargo that has the electrical fault, but it could also be the ship electrical equipment that's causing the fire. And why do we have a fire in the battery? And the fundamental issue with the lithium-ion batteries is that we do have a flammable and chemical unstable electrolyte that is used in the lithium-ion batteries. And outside of the safety windows, the triggered mechanism can be triggered, so it becomes an uncontrollable state. And it could be that the voltage is unstable or that the temperature is out of its safety window. So during a thermal runaway, the temperature inside the battery will increase, and rapidly toxic and flammable gases can be generated. And from these chemical processes in the reactions in the cell, many of these gases can also ignite. And fires that starts in the traction battery, as I said previously, still it's rare, but we also have, it's not as reported in the statistics. I will show you some pictures later. But once the thermal runaway has started, it's actually hard to stop it. You need to cool it, and I will also talk more about this a little bit later. This safety window, we need to have it controllable. So therefore, the vehicles that is used, we need to have safety systems. And you probably heard of the battery management system, the BMS. This monitors and controls many parameters in an electric vehicle, like the voltage and the temperature, the state of health, the depth of charge, and the total number of cycles, etc. There's also a thermal management system, which adjusts the cells to the right temperature by cooling or by heating. And with this, we can totally have the cells in its safe operating window. So looking to the traction battery or the high voltage battery, except the electrical causes that every vehicle kind of have problems with, we don't really know, of course, why EV start fires. It's really hard to find the exact cause. But when I talk to vehicle manufacturers, they mention mainly the two causes that is listed here. We do have the physical damage and the production fault. And the production fault is actually kind of always there, but it's getting, of course, less and less common as you have several safety checks before the battery and the vehicle leaves the factory. And that's why we also have, for example, the BMS, and will alert in the driver display what is trouble with the vehicle, or even stop the vehicle for driving if there's a problem. The other harm that can cause the thermal propagation is the physical damage. So some kind of intrusion into the battery and having the instability of the voltage or the temperature or some anomaly. So this could also be from a crash or collision. Of course, it could also be an external fire that is causing and spreading to the electric vehicle. Even I am not a battery expert, but we do have a lot of batteries out there. Lithium-ion batteries are today one of the most used batteries in different types of equipment, for example, the vehicles. And this is because lithium-ion batteries can store a lot of energy, and it's highly attractive of this kind of high performance applications. Of course, there's no emissions during use, but there's also a high energy density in these kinds of batteries, and you can get a high power output with rapid charging. So there's a big family of batteries, and they have different shapes and properties, and the technologies is still developing. So we need to learn and keep track of the news and pros and cons of the different types of batteries. As for vehicle industry, I noted that both solid state battery and sodium-ion batteries are coming into prototypes, and we will see how this will affect the fire safety. So I was asked to talk a little bit about the myths regarding the electric vehicle fires on roller ships. And these are some of the myths that are out there, and I hope I can contribute to the understanding. So firstly, as I told you, the statistics, the data is sometimes hard to find. However, I frequently also get the question, why do we actually have, I mean, can a fire start in a parked vehicle? And yes, as you can see in the figure to the left here, we have almost 50% when the vehicle was parked. And to the right, you can see that there's also about 50% that is unknown. So we don't really know where the fire started. In Norway, they have a large fleet of electric vehicles, and you can see here the number of vehicles and also the number of fires during 4 or 5 years in the 2016 to 2021. And still there's the number of electric vehicles is lower to the petrol and diesel vehicles. But if you also normalize the numbers, so you can see that there's a lot of petrol diesel fires, but also some EV fires. And if you normalize it, we can see that there's a factor of 8 less common with an EV fire if you compare it to the other vehicle types. And I think in Sweden we have about 10 less common with an EV fires because we don't have as much EVs in the fleet yet. And of course, we need to update these numbers as the EV fleet are increasing. But so far, I would say that there's no more. It's less frequent with EV fires than with fires in internal combustion engines. So looking at what actually burns in a vehicle, then, well, it's actually mainly plastics, like the seats, the panels, the tanks, the cables. We also have rubber in the tires. And the combustible content has, as you can see on this graph, for example, changed over the years of development in the automotive industry. In the 15 and 60s and 70s, where the fire requirements came about in the vehicle industry, there were hardly any plastics used in the vehicles. But as of the year of 2020, it was almost 18% plastics that was included in the vehicle construction. You can also see the weight that has been shifting a little bit up and down, but now we are about the same average weight on the vehicle as back in the 70s. And plastics can burn rapidly and release about the same energy per kilogram as heavy fuel oil during combustion. So when burning, plastic can also melt and it can drip, and this can create small pool fires, which can support the fire spread and build up flames. This research was conducted by the Swedish Environmental Research Institute, and the literature indicate that the highest increase of plastics was actually up to the year 2000, but you can still see some small percentage increase every year. So now that we know that plastics is a heavy part of the energy in a fire in a vehicle, we can compare the internal combustion engine with battery electric vehicles. And I don't know if you're used to see this kind of graphs. I will see. So in this graph, we have two types of vehicles. We have the internal combustion engine, which is the pink one, and then we have two battery electric vehicles that is also burning. And when we measure the heat release rate. So this is the heat that is released during the fire, and we measure it over time. And even if this is only one graph, I can tell you that they look quite the same. The peak heat release rate of any vehicle fire is around 5,000 kilowatts. It could be a little bit lower or a little bit longer. And you can also see that the fire is lasting. If it's no chance of fire spread, a vehicle fire is typically lasting for 1 to 1.5 hours. It could be some difference in the beginning, and this is depending on where the fire actually starts. So for the fire starting like in a petrol vehicle with a gasoline tank, for example, if this tank is involved in the beginning, you will see this rapid increase. With the battery electric vehicles, we can see a little bit slower increase in the beginning, but still they will reach about the same peak in the end. So to the left here, I could say that the fire growth rate, so as you can see here, how it grows, this is not faster for battery electric vehicles. They look about the same. The peak heat release rate is also about the same. And the total energy that is released, well, that is mainly from plastics and not mainly from the actually power source, even if it's gasoline or if it's the battery. And the energy, you can calculate it by kind of looking at the area under the graph. And you can also compare. So we have 30 liters of petrol, that is about 1 gigajoule, and the plastics in cars is 3 to 7 times more. I would also like to mention something about the state of charge in the lithium-ion batteries. And state of charge is not the same as the display charge, as you can see in the driver's display. And generally in the research say that the lower state of charge is safer than a higher state of charge. That's why we want to transport batteries or vehicles with a lower state of charge. However, some recent research has also shown that it might be that higher state of charge actually make the heat that leaving from the cell can leave as mass instead of conductivity through the material. So with a higher state of charge, it might be possible that more amount of energy is released through the mass, and this will actually have a safer impact on the thermal propagation scenario, because the heat will not propagate, through the batteries. But still, this is very recent research. So I would say that EV fires are not more intense than internal combustion engine fires. Okay, looking at the fixed water fire extinguishing systems, we have investigated both water and carbon dioxide. And I tried to have some pictures here. In the top, you have the internal combustion engines, and in the bottom, you have the battery, the electric vehicles. And here is also the same graph, not the same, but you measure the heat release rate. And we can see that when the water was on, so when the drencher system was on, you can see that it's suppressing the fire almost as good for the conventional vehicle as with the electric vehicle. And for both cases, you can see that the fire is kind of regrowing after the water is turning off. So we could say that the water has as good effect of fires on EVs as on internal combustion engine vehicles. And as also was mentioned, we are now conducting a study where we investigate the carbon dioxide performance of battery electric vehicle fires. And this has not been done, what we have found so far. Some research say that carbon dioxide might not be the best medium actually for cooling and for stopping the fire, but mainly this is small scale fire suppression tests. And we did incident study where we were looking for open public fire investigation reports on the vehicle carriers, and we found 22 severe fires that was having a open report, and half of them had carbon dioxide discharge, and that was reported in the report. However, we only found one fire that was started in an EV, and no other electric vehicles were documented in these fires. What we could see here is that there are, of course, some troubles. We do have a long time to discharge, and this is making the fire spread, which then we do have a problem with the heat and the risk of a secondary fire, for example, in another fire zone. And if we do only have one shot of carbon dioxide, this might be a problem. So drencher, yes, we can control it. High expansion foam, we don't have any experience, but we have colleagues or research that is conducted in Japan, and they should carry out, or they have carried out studies on the high expansion foam, and they will release a report, they told us, soon this year. Here is I know Mady will talk a little bit more about this, but as we know, it's really hard to get into the battery, but this was also part of the safety measure, right? So we will not have any instability because the battery is really well covered. So how should you actually fight a fire? Well, our first number one is that you should start a fixed firefighting system without delay. With water, this is easier, of course, than with carbon dioxide or foam. And you should remember that the traction battery is not always involved, is very rarely involved in the fire in the beginning. And you should focus on extinguishing the actually car fire and don't let it spread. I also had a slide on the electrocution because this has been a myth, and it was not us that conducted this study, but we know that the battery has another current than the power grid, so therefore it's kind of very hard and almost impossible to have the electrocution while you're fighting the fire with the water hose. But it's always recommended to cut the power if you detect any anomaly in the battery or in the electric vehicle. We have investigated the smoke toxicity, both from vehicle fires in general and from battery electric vehicle fires. And yes, there are several acute toxic gases released from any fire, actually. It's the gases that you normally die from. But we can fight them, and the water is also washing out the toxicity. Hydrogen fluoride has been, what we have seen is the most biggest difference between the two vehicle types. So you have a higher concentration of hydrogen fluoride in the gases from the EV than from the internal combustion engine. And we also looked into what fire suit you should have. Are actually the SOLAS recommended fire suits good enough? And yes, if you use the EN 469 2020, this is kind of the highest rated, and you should use the level 2, then you should be protected. However, we have also heard now from rescue services and that you can still have a smell. So I guess we need to work a little bit more on the fire suits and the outfit. Even if it's safe for the protection, it might be other risks and this toxicity or the smelling that is not as nice to have on board. Well, it was also a question about the explosion risk, and this is a tricky question that I don't have an answer on, but we do have a small study that is investigating what is the risk of explosion if, for example, the battery is extinguished or the fire and the flames is extinguished, but you can still release the gases that is released from this battery cell. Is there an explosion risk or is it not? Or is the large space actually good in this kind of scenario? We also have working on early detection, which is of course really important, and then everyone wants an early detection, even if it's an conventional fire in a vehicle or in the battery electric vehicle. So as a summary, the risk differ and all vehicle fires are dangerous. Lithium-ion batteries have some specific hazards that we still learn. And we have learned to handle traditional fuels, and we will probably learn also how to tackle the lithium-ion batteries. This is my last slide, so I thank you for the attention.
Yeah, it was very informative. We have got some questions through, but we will pick it up in our panel discussions. I will pass it on to Mejdi now. We will cover the topic on safe carriage of EVs on board vessels. To you, Mejdi.
All right. Thank you, Vinay. And can you stop sharing, please? Thank you. So thank you, Anna, and hello, everyone. My name is Mejdi Kamoun, and I'm Principal Engineer at ABS Technology. I'm glad to be part of ABS, which is a prominent classification society dedicated to enhancing the safety of fire and property while safeguarding the natural environment. So our mission driven approach ensures that we stay at the forefront of maritime safety and environmental protection. And today I'm excited to share some insight of the best practice for transporting electric vehicle on board vessels. So let's delve into each of these aspects in details to understand how we can achieve these goals. So over the past few years, ABS identified the increasing concern with the vessel carrying electric vehicles. I will begin by outlining the key safety concern associated with transporting EVs. So as Anna mentioned, with the introduction of recent technologies in the automotive industry, there has been an increase in the number of electric vehicles being manufactured. Within the past 10 years, EV sales went from an estimate of 10 million to 14 million, with a 53% increase from 2022 to 2023 alone. And it is projected to increase within the next 10 years. Electric and hybrid cars use various types of battery chemistry, each with its own advantages and applications. Here are some of the most common ones. We can find nickel metal hydride battery, which often used in a hybrid vehicle due to their reliability and longer lifespan compared to other type of batteries. On the other hand, the most common chemistry in battery electric cars is the lithium-ion battery, and specifically lithium iron phosphate and lithium nickel manganese cobalt oxide, the NMC, which offer high energy density and is used in long-range EVs. In ABS rule, in our rule, electric vehicle refer powered by lithium-ion battery or similar chemistry, which involve hybrid electric vehicles, plugged-in hybrid electric vehicles, and battery electric vehicles. So, in the context of batteries, thermal runaway is a chain reaction within the battery cells. It starts when the internal temperature of the battery reaches a point that triggers a chemical reaction. This reaction produces more heat. With the further increase the temperature, causing additional chemical reaction and then even more heat. This cycle can lead to extremely high temperature, potentially causing the battery to catch fire and maybe explode. The main cause of the thermal runaway are the electrical abuse. When we talk about the electrical abuse, which involve overcharging or over-discharging to voltage beyond the manufacturer specified charge window. That can cause lithium plating or dendrite formation on the anode. Over time, this may pierce the separator, causing a short circuit between the electrodes and lead to thermal runaway. The other cause is the thermal abuse. Internal temperature in the range of 90 to 100 degrees Celsius will cause the SEI layer to decompose. At temperature above 200 degrees Celsius, the hydrocarbon electrolyte can decompose and release heat. Also, we have the mechanical abuse via penetration, pinching, or bending. The mechanical abuse usually caused by external factor to the lithium-ion battery, such as car crash or during loading and unloading operation. It will result in electrical shorting between the electrode via the electrolyte, producing localized heating. And of course, we have the internal short circuit. An internal short circuit may occur due to the failure of the separator, allowing contact between the cathode and the anode via the electrolyte. This can happen due to any of the previously mentioned abuse condition or as a result of a manufacturing defect. So, how we can mitigate the electric vehicle fire? The mitigation involves several strategy and technique aimed at preventing the thermal runaway, ensuring the safety of the vessel and the crew. Here are some key approaches. The first line of defense against the EV fire is the early detection. By using advanced sensor and monitoring system, we can identify potential fire hazard before they can escalate. This system continuously monitors the temperature, the gas release of the EV batteries, providing a real-time alert to the crew. Prevention of the spread is also a very important mitigation factor. Once a fire is detected, preventing its spread is crucial. This involves designing and implementing effective strategies. By isolating the affected car or the area, we can contain the fire and preventing it from spreading to another compartment of the vessels. Suppression. In the event of a fire, rapid suppression is essential to minimize the damage. This can be achieved through the deployment of fire suppression system, such as water mist sprinkler or other combined fire suppression system. The fire suppression system are designed to quickly and effectively cool down the battery on fire, reducing the risk of thermal runaway propagation and further damage. And finally, after the fire has been suppressed, preventing reignition is a very important step. This involves cooling the affected area and continuously monitoring it for any signs of residual heat or smoldering. Implementing post-fire inspection protocol and using thermal imaging camera can help ensuring that the fire is fully extinguished and prevent any potential reignition. So, due to the increasing number of fire incidents of vessel transporting electric vehicle, ABS recognized that there is a need to develop a collective set of best practice. Back in June 2022, we hosted a virtual workshop where representatives with experience in the transport of this vehicle were invited to participate, and they shared their experience. Attendees in the workshop represented car manufacturer, ship owner, ship operator, flag states, and independent consultant. The workshop participants were asked to complete a pre-workshop survey that queries best practice using transporting EV at the sea. The outcome of this workshop resulted in developing this document. The best practice within this document applied to RoRo vessels, including passenger carrying vessel, pure car carrier, and pure car and track carrier, PCTC. This practice, this is a very important note and point. These practices are meant to complement, not replace, existing measure for carrying of EVs and should be applied according to the configuration of each vessels. The best practice identified during the workshop include vehicle stowage, charging, fire detection, crew training, firefighting, and other special consideration. So on the PCC and the PCTC vessels, it is essential to allocate a designated area for the stowage of the EVs. This ensures that this vehicle are stored safely and securely during the transit. Additionally, any damaged vehicle should be placed in a specific area, preferably on the weather deck if available. This precaution helps to mitigate the risk and manage any potential hazard effectively. When it comes to charging operation, only ship-owned cable and connectors should be utilized. This ensures compatibility and safety during the charging process. Charging should be conducted exclusively from power sockets that are specifically designed and approved for this purpose. These connectors should have the capability to be disconnected from the shipboard power system at a location that is easily accessible in case the vehicle being charged catch fire. Also, and furthermore, it is recommended that charging operations are not carried out during cargo loading or unloading to prevent any interference or additional risk. To enhance the fire detection in cargo area designated for the electric vehicle, it is important to install a monitoring system such as a video monitoring system. This system will supplement the existing fire detection mechanism, allowing for early identification of the fire location and prompt activation of the appropriate firefighting system. Additionally, the frequency of fire patrol should be increased in area carrying EVs to ensure continuous monitoring and quick response. Furthermore, providing portable thermal imaging device to the crew performing patrol in the RoRo cargo space containing EVs is crucial. This device enables the crew to detect heat source and potential fire hazard early, thereby preventing incident before they escalate, of course. Proper training is also important for the crew member who may need to respond to fire involving EVs. It is important that the crew can recognize electric vehicle, understand the risk posed by the high voltage equipment, and be aware of potential release of flammable and toxic gases. This knowledge is essential for effective and safe firefighting operation. Moreover, and as I mentioned earlier, crew members involved in patrolling area containing EVs should be provided with thermal imaging camera, and they have to be trained on their use. This training ensures that they can effectively use this device to detect and address fire hazard promptly. So, to ensure safety in area carrying electric cars, it is essential to install fixed water deluge system or mist sprinkling system. For open deck area, a fixed monitoring system can also be used. The drainage is to be capable of handling at least 125% of the combined capacity of both the water spraying system pumps and the required number of fire hose nozzles. The required routine inspection are crucial for the drainage system to prevent any clog or blockage of the drainage system. The EV charged on board ferries, it is vital to cut the ship's electrical supply to the vehicle before attempting to fight the fire, and this reduces the risk of electric shock. For other special consideration, all vessel carrying EVs should be equipped with water lancing equipment, which should be easily accessible, especially for vehicles stored in containers. So, after publishing the best practice document, ABS updated our marine vessel rules, specifically the section 5C-10-4, which is related to vessel intended to carry any type of vehicle. An optional notation, EFP-CEV, was developed and included in our rule. Ro-ro cargo space intended for the carriage of the electric vehicle may be eligible for this optional class notation, provided they meet the requirement of the section 5C-10-4/3. This requirement covers fire detection, fire extinguishing arrangement, ventilation system, electrical installation in ro-ro cargo space, and other specific arrangement. So again, in addition to the requirement of 5C-10-4, the ro-ro cargo space intended for the carriage of the electric vehicle may be eligible for the optional class notation, provided the following requirements are met. This requirement include when the electric vehicle are carried in the same cargo space as a fuel-powered vehicle, designated area are to be assigned for the electric car and to be marked accordingly. When it is not practical to store this vehicle in the designated area, the requirement is to be applied to the entire cargo area. So also an additional requirement, a video monitoring system is to be installed to supplement the fire detection system for the cargo area. The video display is to be located at the navigation bridge or the fire control station with immediate playback capability to allow the identification of the fire location. A minimum of 2 portable thermal imaging devices are to be provided and stored with the firefighter's outfit for use by the crew performing patrols in the ro-ro cargo space. The thermal imaging device are to comply with the recognized standard, for example, the NFPA 800-01, and certified by a certification organization recognized by the applicable standard. Again, a fixed pressure water spray system is to be provided for the designated area in the ro-ro cargo space carrying electric car. 2 additional sets of firefighter outfit are to be provided for ro-ro cargo space intended for the AV carriage. They are to be stored in readily accessible location near the designated area in the cargo space. In addition, and when where installed, electric equipment, wiring, and power socket are to be used to supply power to the electric vehicle, and are to be a certified safe type for use in an explosive environment. Electric cable associated with charging of electric vehicle are to be suitably protected even when armored. Finally, ABS always can consider alternative arrangement to this requirement, provided they meet the intended purpose and offer an equivalent level of protection. A risk assessment can be conducted to establish that the alternative arrangement provides a same level of safety. So if you would like to access to our rule, please visit our website. And if you have any question regarding this presentation or our rule related to this topic, please feel free to contact me via my email or reach out directly by phone. And thank you. That's it.
Thank you, Mesri. That was very informative and quite a detailed presentation. Right. So we are going to have a panel discussion where we are going to discuss a kind of Q&A sessions with the panel relevant to the topic. To start with, I would like it is to you, Seb. With your background, the decade of experience dealing with lithium-ion batteries, and also in your current role as Managing Director of Maritime Battery Forum, can you share your view on how the safety of lithium-ion batteries have evolved over the past decade and its rapid adoption within the maritime industry?
Yeah, thank you very much, Vinay. So over the years, we've seen quite some different incidents with batteries on board ships, both batteries as part of the propulsion system, but also batteries as part of the cargo. And thanks to sharing of experiences with those incidents, we've managed to learn quite a lot from those incidents. We've learned about thermal runaways, how they propagate, and how to properly insulate them to prevent propagation. We've learned a lot about different firefighting methods and procedures, and we've learned a lot about ventilation and how to prevent explosions happening from the gases being released by the batteries. Many of these incidents were caused by external factors. So it's not just the issues, any issues from the batteries themselves. It's also all the things that are around the battery. So it's important when discussing battery safety to also pay attention to the risks to the batteries and not just risks from the batteries. So battery safety is still a very important topic to discuss. And it's not because batteries are not safe, because when you understand how to design and integrate or transport batteries, it's absolutely possible to use them in a safe way. Whether the batteries are part of the propulsion system on board or part of the cargo, it is always important for all the people involved to be aware of the design safety functions and how to act in case of an incident. So therefore, the input from classification societies like ABS is important, for instance, considering rules for propagation insulation in case of a battery fire, but also the work from research institutes like RISE really helps us to understand what the right safety functions are for which types of situations. We are not yet at that point where all of this is common knowledge along all different levels within the industry. So we need to keep on sharing information through events like this today, and keep on developing our knowledge and understanding of safety related to batteries on board ships by sharing experiences from incidents.
Thank you, Ted. That was very detailed and a great review. I mean, it's the evolving risk, and we as end users and or the carriers of this risk. I think that there's a lot to learn as the technology keeps growing. So I have one question to Anna. Current statistics indicate that the possibility of BEV fire is lower than a fire in ICEVs. Is it safe to say that carriage of EVs on board poses lesser risk than ICEVs?
Thank you. Well, it's a tricky question, and I like the Sid, what he was talking about. We still need to learn and understand. So, I mean, today we can say that, well, the fire to start in the battery, we have a lower probability for that case. But of course, this is, we need to balance that with maybe the consequence. We don't know to handle maybe, or we can't stop the propagation. So I saw in the questions here as well that like the consequence of a fire might outweigh the lower probability, but yeah, so I don't have a direct answer actually, but in general I would say that the electrical causes are more are a higher risk, and this is independent on the power supply. So we do have about the same we do have the same energy that can be released during the fire, independent on if it's an electric vehicle or if it's an combustion internal combustion engine vehicle. So I'm also sure that we would be able to handle them safely if we continue to learn and understand everything.
Thank you. I also have a question for you, Anna. Two questions, but maybe I can combine it into one. Do you need to take different precautions based on the type of battery that you're transporting? And is there a difference in safety between old and new batteries?
Yeah, good questions. Well, so looking at the electric vehicles, I would say that we and the industry, as also MEDI, we want to have kind of the same approach. It should be easy for the crew to handle the fire if it's starting. So whatever, independent on what power source it is, we are aiming for the same like intervention in case of fire. What we can see looking at the vehicles, as I said, solid state batteries is coming into that industry, and also sodium ion. So here it might be actually that the sodium ion batteries can be transported with a lower SOC, maybe down to 0 SOC, and that would maybe, you know, be a safer state to transport them in. So at the time being, I would say the lithium-ion batteries might have the higher is more risky than the other, like the batteries technologies that is coming. They are currently always working with the technologies making them safer. So we should not take, well, I'm mostly into electric vehicles actually, but transporting, as I know on container ship also, and as like transporting the batteries as a cargo, well, we always need to understand what is this type, and there's a lot of UN numbers coming, for example, on the different types of batteries that is transported. So in that case, yes, but looking at the electric vehicles, I hope we can use the same. Well, old and new batteries, this is also lot. I mean, you can have different views on this. Looking at the aging, for example, there's a lot of discussions going on and research as well. And with materials in general, it's a kind of degrading process that is going on. And for the batteries, you can have a chemical or physical aging, like the reactions inside the battery, which can, of course, decrease the performance and the capacity and some safety issues. But we have the state of health that is monitored through the BMS, and the battery in the vehicle will probably never be like, you don't need to worry to have that to have the safety issue, because the state of health is monitored and you will not be able to drive the car. I know it's a discussion also with like second life batteries, or transportation of them, well, old or second-hand vehicles and stuff like that, and that is of course a tricky situation, because we don't know what vehicles has been what has happened in their lifetime. So that is still going on, I would say.
Thank you. Then shall I move on to Meshti? Vinay, is that okay?
Yes, please.
Perfect. Meshti, for you, how important is monitoring of the batteries to ensure safety, and what are the possible methods to monitor the batteries on board?
Yeah, see, monitoring battery is very important. As Anna mentioned, there are different techniques to ensure the safety, and it helps detect the potential issue early, such as one of the most common technique of monitoring is detecting the overheating and the release of flammable and toxic gas, which is in the early phase of the thermal runaway. This proactive approach can prevent battery failure and cascading event, and thereby reducing the risk of an incident. Again, the most common technique for monitoring include gas, smoke detector, thermal monitoring system, and the most simplest one is, of course, regular fire patrol. However, there are other advanced methods available, though not all are equally suitable for onboard installation due to their complexity and the cost. For example, a tracker installed in each car and connected to the BMS can provide detailed insight into the battery degradation, and of course allowing fleet manager to monitor battery health over time. This capability enable rapid intervention but again, as I mentioned, while this advanced method offer significant benefit, their implementation can be a little bit challenging in our time and at the present, and very expensive, which make them less feasible for marine application.
Thank you. And then I have one more question for you, more on the ship design. So do existing car carriers need to be updated or retrofitted to be suitable for transporting electric vehicles?
Definitely, Sib. Yes, the answer is yes. Existing car carrier often used to be retrofitted to safely transport electric vehicle. EVs, as we all discussed, have a unique requirement due to their battery system, which can pose additional fire risk if not properly managed. Retrofitting can include the installation of dedicated fire suppression system, enhanced ventilation, also temperature monitoring equipment to ensure the safe transport of this vehicle.
Thank you, Mejdi. I've got one question for you.
Sure.
For emergency preparedness, crew training and awareness regarding the lithium-ion batteries risks and associated fire risk basically is very important. So what's ABS perspective on the existing training standards, and are there any gaps that require improvement in the training standards?
Sure, very great question. ABS emphasize on the importance of the crew training and the awareness regarding the risk associated with the lithium-ion fire. Crew member should be trained to recognize what type of EV are on board, understand the risk posed by the high voltage equipment, and be aware of the potential release of toxic and flammable gas during a fire. Training also should include the use of devices such as thermal imaging camera or other specialized fighting equipment. Back to your question from ABS perspective and about the existing standard, the development of training standard is definitely an area that require improvement. We have one significant gap is the need for more comprehensive training standard or programs that cover the latest progress in battery technology and the fire suppression methods. Also, and additionally, regular drills and updated protocol are essential to ensure that the crew member are well prepared for emergency in case we have incident.
Thank you. I think that's very well explained and very well answered. Okay, I think I've got, we have no further questions for the panel. So we are going to move to Q&A session with the audience. I think I've seen quite a number of questions in. So we'll pick a few questions from here. There's one to Anna. What is the weight difference between ICEV versus BEVs? TNE calculate this to be average 300 to 400 kilograms heavier per BEV. Does this align with your findings?
Yeah, I would say we have done some measurements in some when we do have fire tests, for example, and we have noted that like a EV of the same size, like a passenger car or so, is approximately 20 to 30% heavier compared to the conventional vehicle. I don't know if that is corresponding to 300, but 300 that would be around the same, I would say. If you say that we have a 1,000 kilo vehicle, so that is aligning.
Thank you.
Thank you.
Okay, this one to Mejdi. What is the rationale of storing EVs in one area? In near future, we only have EVs on board PCTCs. So this precaution is not going to be valid. I think it's a very interesting question. Yes, to you, Mejdi.
Yes, our requirement applied to the present, and here we're talking about the segregation of the electric car from the conventional car. The segregation of provide a dedicated area for the electric car is important. We don't want to have additional fire hazards getting close to the electric vehicle. That's why designated area and the segregation of EVs are very important in from our perspective.
Thank you. There's one more, I think, to you, Mejdi. What detection system is capable of warning a crew of a lithium-ion EV fire timely enough for the crew to operate CO2 or other within a period of less than 15 minutes before any other car is burning?
So, as I mentioned earlier, the most common fire detection system is to detect the first phase of the thermal runaway, which is the gas detection. It can be smoke detection or thermal sensor that can detect that there is temperature raise. These are the most common detection system that we can use to for early detection. There are also, again, as I mentioned, more advanced technique. They used connecting the BMS to send a signal to the PMS and the EMS of the vessels. But here we're talking about feasible in terms of application and deployment on the board of all the car carrier.
Yeah, I think thank you. There's one to Anna. I think it's a very generic question, but hopefully you can answer that. Recognition of lithium-ion battery fires is a known hazard. How can we mitigate this? I think it's a very generic, open question.
Can you say that the reignition? Do you?
Yeah, reignition of lithium-ion battery fires. Yes.
Yeah. It's an open question, of course. I think here we need to have help from the vehicle industry and the automotive industry, and we know that they also want to have safe vehicles, right? For them to be able to stop the propagation, like inside the pack, or to not let the cell propagate to more than one cells. That is would be like coming to the root. Then reignition will be there if as of today. So mitigating is having it cooled. I think on board a vessel this is really a tricky question. So I know that the fire blanket is not it's not stopping the reignition, but to help prevent fire spread and to help it keep it in a safe mode. That could be one safety measure.
Thank you, Anna. I think we'll take one more questions. I think we have passed an hour mark. What about large-scale battery storage units, which may be carried on other vessel types? Is there any work being carried out on safety measures for this? I think this is probably to Seb.
Yeah, so I assume this is more related to the battery systems integrated into all different types of ships, if it's hybrids, plug-in hybrids, or full electric.
Yes.
Yeah, so there's much work also going on the development of all these rules related to this, much of it coming from class societies and other organizations aiming to increase the safety on board battery-powered ships. And although there are some differences because it is you design it from the ground up to be part of the ship, so it's easier to integrate the battery monitoring or the battery management system with the alarm systems on board the ship. Much of the safety aspects are the same. So you want to monitor the batteries so that you're able to release firefighting systems as soon as possible. You want to have containment of the fire so that the fire doesn't spread to other batteries or other parts of the ship. And you want to make sure that there is sufficient ventilation so that if there's gases coming from the batteries, that these are not kept in a confined space, which can lead to explosive situations. So although there might be some differences in how to approach it, because it's part of the ship design, still you want to take care of the same measures.
Thank you. Thank you, Seb. I think we'll take one more final question and then probably we'll have to call. But the questions which we are not able to take now, we are happy to take it over the emails and we will definitely get back to you on that. This is for Mejdi. Oh, yes. There's one gentleman who would like to inquire about any potential or current regulations on the maximum charge of EVs on board for transportation, as there are already a current maximum charge allowance of Greek ferries of 50% charge. To Mejdi, do you have any?
No, our current rule doesn't mandate or require to limit the state of charge of the EV during the transportation. The thing is, we develop more stringent notation, more stringent than the actual optional notation that we have right now. We receive pushback from the shipyard because all these requirements are very hard to implement. But we are working with different entity to enhance our requirement and develop it further for safety reason, of course. And one of the discussion is to limit the state of charge of not only the EV, of any energy storage system based on the lithium-ion battery. So, and we're talking about the range of 30 to 40%. So yeah, there is a discussion going, but there is no actual rule or requirement that mandating to limit the state of charge.
Thank you.
Sure.
Okay, I think with this, we're going to conclude the webinar. I would like to take this opportunity to thank everyone for joining us today. We hope you found the discussion insightful and informative. A very special thanks to the panels for sharing their insights and expertise on the topic. If you have any further questions, please don't hesitate to write to us. We value your feedback and would love to hear from you. And also remember to check your email for a link to the recording of this webinar. And we appreciate your participation and look forward to seeing you at our next webinar later this year. Have a wonderful day.